Okay, hi. I'm Ellen Buckley, and I've just finished my first year as an assistant professor at University of Illinois. And my work has been focused on remote sensing of sea ice in a lot of different ways. And so I'm going to talk about some recent advances of new remote sensing technology and how we're using that to understand changes in sea ice. Here's my blank slide. Okay, so we've seen this. We've seen this a lot, so I don't really need to explain it, but we're seeing decline in summer sea ice extent. And I do want to point out, though, that this is from a 46-year record of passive microwave sensors starting in 1979. And we've seen a lot of advances in the passive microwave sensor technology. So starting off with the simmer sensor in 1979, and then over time we've had new channels added to passive microwave, and we've been able to get more information and correct for known biases and improve resolution of the passive microwave data. And so this is showing the 25 kilometer resolution passive microwave extent, but now we have much higher resolution. But we do have a long-term record of this 25 kilometer passive microwave sea ice extent. We're also seeing other trends in Arctic sea ice thinning, drift speeds increasing, changes in the makeup of the sea ice, so transitioning from what used to be predominantly multi-year sea ice to now mostly first-year sea ice. And I also like this representation of the sea ice extent, so kind of depicted in the same way, but we're seeing our lowest sea ice extent in basically all years, or in all months in recent years. Same thing for, well, not the same thing for Antarctic, but the same figure for the Antarctic. Also seen this figure many times this week. So briefly, some of our highest Antarctic sea ice extent, and then some of our lowest sea ice extent more recently. Showing here global sea ice extent. And then again, this visualization I think really pulled out the interesting Antarctic patterns of high sea ice extent and then low sea ice extent. Yeah, so just wanted to point out changes in sea ice extent, thickness, trends, kind of on all fronts, and a lot of things to observe with satellites. And these are some not totally comprehensive ways that we look at sea ice data from remote sensing. Here showing all satellites, but I talked about passive microwave data for sea ice concentration and extent. Also can tell us a bit about ice type. It can give us the thickness of thin sea ice. More recent, I mentioned those new channels. Now we can see different channels and getting different ratios that can tell us about snow depth on sea ice, kind of shallow snow depth on sea ice. And then also doing cross-correlation of passive microwave data to get sea ice motion. Altimetry, we can have sea ice height, and then from heights of the sea ice and heights of the sea surface, we can get freeboard estimates of thickness, allow us to get, or estimates of snow depth allow us to get thickness from altimetry. Scatterometry, we can look at the backscatter and determine sea ice type, and again, look at sea ice motion. And with synthetic aperture radar, ice type, ridge detection, lead identification, some newer high resolution observations from synthetic aperture radar. And so now I'm just going to, oh, wait, no, I'm not there yet. Talk about some different sea ice processes at different scales. So sea ice processes span from these really small scale processes, both in terms of spatial resolution and also temporal scales. So there's these really small sea ice processes like the microstructure of sea ice and how the brine melts through the ice, and then going up all the way to these big teleconnections, anthropogenic change, and then everything in between. So I've been particularly interested in ponds. So you can see these pond processes occur kind of in the in-between scale, kind of going between this purple section and this green section. The purple section is what we can measure from remote sensing, and this green section is more the scale of what we measure in situ. So there's a lot of different processes that span many scales, and it's important to be able to look at all of these processes from both remote sensing and in situ and airborne remote sensing as well. So as we have new capabilities, we have higher resolution data, so higher resolution sensors on satellites. So this, in this direction, we're getting higher resolution data from this purple section moving inwards to this green section from satellites. And then also with more satellites, we're having more higher temporal resolution because we're getting more satellites that are measuring the same sea ice. And so we're increasing the temporal resolution of our observations as well. So I'm just going to go through some examples of what we can see with new technology from sea ice remote sensing. This is ice from IceEye, so that's a commercial SAR satellite series. And this is an image. I'm not sure why it's in blue color scale, but you can kind of see the different ice flows here and the different types of ice if you're familiar with SAR imagery. But they used these data to navigate through the Weddell Sea when they were looking for the Endurance ship back in 2022. So this was at in the Weddell Sea, and they used these data to be able to differentiate between multi-year ice, first-year ice, and leads, and find a way to get through to where they ended up finding the ship. This is an example from a project based on mosaic data. And so from this, they were, I'm sure most people here are familiar with mosaic, but ship-based campaign to measure like Lagrangian changes of sea ice over, well, this obviously is in the summer, but monitoring these small-scale melt processes on a single ice flow. And they were also able to task the Planet Lab satellites to be able to capture images when there's clear skies of the flow and monitor it from a larger scale too. So on the right-hand panel, you can see the same flow, the same location, but this is the beginning of July, middle of July, and end of July. And you can kind of see how the ice has evolved. And this melt pond here has almost completely drained. This is an example from a recent paper, first look at SWOT. So SWOT is the Surface Water and Ocean Topography satellite that was launched in end of 2022. And it has two swaths. So there's two swaths, and then in the middle there's like a JSON-style radar altimeter that measures higher resolution altimetry. But overlaid on this, you can see these two SWOT swaths. And then on top of that are the ISAT-2 lines. So that's a high-resolution, a long-track photon counting laser altimeter. And here they've compared these high-resolution ISAT-2 heights with the SWOT data and have found good agreement. And you can kind of see the importance of that finding because SWOT has a much larger coverage. So instead of just a long track data, we have now these like huge swaths of these three-dimensional sea ice data. And SWOT, I should mention, it has an inclination of like 77 degrees, so it doesn't fully cover the sea ice, but is good for some marginal ice in the Arctic and also Antarctic sea ice. But it's really has a great potential for increasing our altimetry measurements of sea ice. This work, now I'm kind of getting into some of my work, and I'll go into detail about these new high-resolution measurements of sea ice that I've been working on. So this is worldview imagery, and in the winter, I think this is like late March or April, and on top of that are the ISAT-2 lines, so you can see these linear passes across the image. And this is a kind of a small-scale image, so 4 kilometers. ISAT-2 has a footprint of 11 meters, and so it can resolve really small leads and fractures within the ice cover. And so here we're showing an image classification routine applied to the image. So red is ice, the royal blue is open water, and the light blue corresponds to this new ice. You can kind of see it's like a little bit grayer in color up here. and then corresponding to the cyan. And ICET2 has a surface type classification. So based on the return characteristics of the photons within an individual ICET2 segment for sea ice, it can it can determine what type of surface it is seeing. And so here I've also maybe this is making it more confusing, but colored the ICET2 in the same way that I've colored the image. And so you can see as this ICET2 pass goes over this small fracture, there are segments in here that are classified as open water. And so it's able to resolve these small leads and perhaps pick out some open water areas that previous altimeters definitely were not able to detect, and then also other satellites won't be able to see either. And then also we've used ICET2 to look at melt ponds on sea ice. So this is a work that we did looking at melt ponds in the Lincoln Sea. So this is a bunch of imagery here. So this is Sentinel-2 imagery, MODIS imagery, and then ICET2 tracks over the month of June on this Lincoln Sea region. And then pointing out all these different melt ponds that we were able to detect from the ICET2 photon clouds. So I mentioned ICET2 is a photon counting laser altimeter. So the response, I'll get more into this later, but the photon cloud is what the sensor sees, and so that from that data we're able to pull out melt pond properties given ICET2's very small, relatively small footprint compared to other satellites. Okay, so getting more into the specifics of some of the projects that I've just started talking about. So this project we're calling the linear ice fraction because we're using ICET2, which is in a long track, one-dimensional measurement of the ice cover. Between ICET2's 6 beams, you have 6 tracks across a given area of ice. And so it's one-dimensional, and we're thinking of it as like the one-dimensional equivalent of sea ice concentration. So from that surface type classification, we're able to determine what percentage of this track is open water and what is ice, and pull out this linear ice fraction product. And this was motivated by the fact that this is 25-kilometer passive microwave data. And you can see, and this is the color bar that's maybe kind of hard to read, but you can see most of this area is 100% sea ice concentration, but when you look at imagery, you see a lot of fractures in this sea ice. And so what that means is that if you're doing studies thinking about like the heat momentum transfer between the ocean and the atmosphere, you're missing out on all these little fractures that really do enhance the amount of heat and momentum transfer between the ocean and atmosphere. And so we're looking to maybe understand where passive microwave isn't as good as having a higher, like where these high resolution measurements of these fractures in the ice are not detected in passive microwave data, and using ICET2 to do that. So first we decided to look at passive microwave data to see where it is. This has become a much bigger project than where it started, but thinking about where passive microwave data is biased, what different products of passive microwave data we have. We're looking at a few different products. So the NSIDC is the NSIDC climate data record. So this is a passive microwave data that is shown in all those CDR long-term trends. And we're using that because that's like a standard. That product is made up of the Bootstrap and NASA team algorithm. So we're looking at both of those as well. And then this one is the AMSR-2 satellite with the NASA team 2 algorithm applied to it. Then we have OCSAF and then AMSR with the ARCHIS sea ice algorithm applied to it, which is higher resolution. And so to determine where passive microwave maybe isn't picking up these small scale features, we look at high resolution imagery. So this is a map of a bunch of flights from Operation Icebridge. The green is wintertime data, and then the orange and the blue are summer data. And so using that algorithm that I showed on the previous slide, we've applied classification algorithm to determine where the sea ice is, the open water, and in this case, we're calling the new ice as ice, and the melt ponds also as ice for sea ice concentration purposes. And so when we compare, obviously the passive microwave grid cells are much larger than individual images. So we're looking at individual images that are all within one, averaging that out and comparing that with the passive microwave data from that day. And so when we compare these two passive microwave sea ice concentration and the concentration from the imagery, we find that in the winter time, this is a top plot, passive microwave data is biased slightly high, so a few percentages above the true passive, or the true sea ice concentration from the imagery, except for NASA team, which overlaps with the zero bias. And then in the summer, interestingly, also biased high, and then NASA team has a very large spread here. So yeah, we definitely had to work through some of these specific biases here, but yeah. There does exist a good bit of bias in the summer, and in the winter, this might not seem like a lot, but when you're thinking about whether you have 98% sea ice concentration or 99% sea ice concentration, you're essentially, when you go from 98 to 99, you're having the amount of open water that's available for that momentum transfer. So what we've done to maybe augment or identify specific areas of this passive microwave bias, definitely not replace any passive microwave data for Arctic-wide or Antarctic-wide sea ice concentration, but we've looked at ISAT2 potential for resolving leads and being able to understand where these passive microwave biases are. So I mentioned this before, but ISAT2 has 6 passes, so 3 beam pairs, and has the classifications of lead or ice. And so we're able to look at the length of all the ice segments over the length of all the segments, and then you get the linear ice fraction, or the one-dimensional proxy for sea ice concentration. And so for this particular image, the passive microwave data say it's 100% sea ice concentration, which is fair because these are very small leads. The classified image is 97.5% sea ice concentration, and when we look at just this pass across it, we are seeing that the linear ice fraction is conveniently also saying 97.5, but we're not just basing everything off of this one image. We've built an emulator to look at how ISAT2 samples a two-dimensional image and are able to understand how many crosses across an image we need to get a good understanding of what the sea ice concentration of this area is. And so we've run a lot of tests looking at individual images that we've classified before at a variable sea ice concentrations, and then different samples of the ice surface, depending on the location of the image and the angle of attack of the ISAT2 satellite. And then we found that approximately 11 crossings will get us within the 2% bias. And so we're able to move forward and create a product that for any 25-kilometer area, if there are 11 crossings in a month that are cloud-free, then we can pull out the sea ice concentration or linear ice fraction for that cell and compare with the passive microwave data. Okay, and so that's what we've done here, and we've split it up into summer and non-summer. Right now we're going to ignore the gold part. But so the ISAT2 linear ice fraction shows higher sea ice concentrations for winter and longer tail for summer. And then looking at all of these passive microwave algorithms here and then we do the subtraction of these passive microwave sea ice concentration minus linear ice fraction, and we do see these are still biased high, so very consistent with what we found when we compared the passive microwave data with imagery, right? So these data are still so the passive microwave data is overestimating sea ice concentration when compared to the linear ice fraction, if you're calling linear ice fraction the truth. So you have these high right tails, which is biased high, except for this OC-SAF one and the NASA team one, also much lower. There are a lot of limitations of the linear ice fraction. So we only calculate linear ice fraction where there's 11 passes of cloud-free data. It also has to be, the ICESat-2 product isn't created until there's at least 15% sea ice concentration according to the CDR. And so we have a very limited amount of data that we can compare with. And so here's just showing mostly in the central Arctic. For obvious reasons, we have high sea ice concentration and a lot of convergence of the ICESat-2 tracks. So we have a lot of comparisons in the central Arctic, and then as you get out to the marginal ice areas, it's not, we can't compare as much. But we do have a lot of data here, and this product is publicly available and might be of interest to compare future work on regionally differences between linear ice fraction and these passive microwave products, and also temporally too. Okay, that's the linear ice fraction work that we've done with this new advance in technology where we can resolve these small scale leads. And now I'm also going to talk about high resolution observations of melt ponds. A lot of collaborators on this project because I've been working on this since the beginning of my PhD, and I'm still obsessed with looking at melt ponds, especially from ICESat-2. And this is my favorite melt pond. It's a smiley face. Okay, so I maybe might kind of make this very brief, but the importance of melt ponds on sea ice, I guess primarily, is that it darkens the sea ice surface, so enhances the ice albedo feedback by absorbing more solar radiation and furthering melts. It's been shown that incorporation of melt pond fraction in models improves forecasts of some extent, so it's good to know different melt pond parameters. Melt ponds are seen as like the skylights of the ocean, so with more light coming into the upper ocean, that affects the ecology and under ice light distribution. They also weaken the ice, making it more susceptible to breakup in summer storms and increase heat and moisture flux to the atmosphere. Some challenges of studying melt ponds is that it's difficult to observe or to measure melt ponds when the sea ice is melting because you're wandering around through these melt ponds and trying not to fall in. A lot of our understanding until recent years has been from the Shiba campaign in 1998 on multi-year ice, where they had in situ and airborne observations of melt ponds. And we've learned a lot about melt ponds from that, but that was very specific and now like 27 years ago. And so more recently, the Mosaic expedition on first year and second year ice, I think, also had similar styles of observations where they looked at melt pond fraction and melt pond depth and followed a flow throughout the summer. And so these two different campaigns allow us to compare and contrast different regions, but they are also limited spatially and temporally, right? So that's why we look to remote sensing observations of melt ponds. And with our new advancements in technologies, we have these higher resolution measurements that can resolve small-scale melt pond processes. However, when we look at melt ponds from space, you do need high-resolution imagery here. So we have MODIS imagery, 250-meter resolution. This is in the middle of the summer. There is melt, but you can't see it. When you look at Sentinel-2, this is 10-meter resolution, so we are getting to the scale of melt ponds, but really you can only see very large ponds in this. You can see some of these like light blue areas here. Worldview is incredible. It is commercial data, it's MaxR, has 2 to 3 meter resolution, but it doesn't have like Arctic coverage and it's commercial, so you have to pay for it. And then we have designated airborne campaigns to take imagery, and there we can see really high resolution melt ponds. So this is like kind of our whole span of melt pond imagery that we can get from remote sensing observations. If you can't fully resolve melt ponds, there will be biases or problems with your melt pond fraction and statistics that you gather about the surface. So here I've looked at, this is Sentinel-2 data and this is WorldView data of the same flow on the same day. And here, if you apply that classification algorithm, the melt pond fraction, now yellow is the melt ponds. The melt pond fraction is 7.6%, but if you look at it in the WorldView data, it's 25.5%. So that's just an example of how important it is to have high resolution data for resolving melt ponds. So one of the projects that we did was we looked at 2 different ice bridge campaigns. So one based out of UIUC in 2016, and then one from Tule, which is now Patufik, in 2017. And so this, if you're familiar with Arctic sea ice, you know these are very different ice regimes. So in this area, we're looking at predominantly first-year ice, and then this area, this is the region of the thickest and oldest ice in the Arctic. And so what we've done with that, we have these 10-centimeter resolution images that look a lot like this. This is Elvis data, but this is, we looked at DMS data, which is similar resolution, 10-centimeter resolution. So we're able to resolve those melt ponds. And so when we apply the image classification algorithm, we can pull out the melt pond fraction from all these images. And so this is the distribution of melt pond fraction from 2017, looking at the predominantly multi-year ice area with a lower melt pond fraction, and in 2016, looking at first-year ice area that has a wider spread of melt pond fraction and larger on average melt pond fraction. And this is not like new, like totally new information. This is just confirming what we already know, is that first-year ice, because the lack of deformation features, the meltwater is able to spread more easily across the surface, whereas on multi-year ice, the meltwater kind of gets stuck in the hummocks or between ridges that have formed over the years of deformation. And this is an important result in terms of thinking about how the Arctic is transitioning from predominantly multi-year ice to first-year ice, and what that means for melt pond fraction and albedo at the surface. We've also been able to look at melt ponds from ICESat-2. So ICESat-2 is a photon counting laser altimeter. So these are what the returns like. So there's a high concentration of returns at the surface. There's some subsurface backscatter, and because it's in the summer and ICESat-2 operates at green light, there's solar background, and so there's just photons that don't really mean anything. And then, so if you're going across the surface and you are going over a melt pond, you will see returns from the surface of the pond and from the bathymetry of the pond. And that's because this unique 532 wavelength can penetrate the water column and give returns from the bottom of the ponds. And this we found in where there's imagery that's been coincident with ICESat-2 passes. We've validated the presence of this melt pond in Sentinel-2 data. And so with the ICESat-2 data, we wanted to create an algorithm where we can track the surface of the pond and the bathymetry and pull out the pond depth, because that didn't exist in the original products. And so what we did here was we created that algorithm and looked at pond depth evolution over the summer. And these are our results, looking at pond depth increasing and then some pond drainage, and then increasing again and becoming more variable throughout the summer. Where's the mouse? Okay. Okay. I might have to skip some things. Recent work, we've looked at how the presence of melt ponds affects the ICESat-2 return, because it's really important to be able to measure the sea surface height and the and the ice surface for freeboard, and then thickness estimations. But we don't currently have thickness in the summer from ICESat-2 because of the presence of melt ponds. That is confusing the algorithm about whether it's the sea surface or not. So we've done work to make sure that ICESat-2 is able to distinguish between melt ponds and the sea surface. I can get into that if you're interested later. But just moving forward, we have a lot of new measurements of sea ice. That's something to be excited about. NISAR will hopefully be launched this summer, Crystal in the next few years, hopefully EDGE. I think Helen's convinced us all of that. And then also, I want to point out that NASA has this commercial satellite data acquisition where you can request data from all these commercial satellites. If NASA's already acquired it, they have like a library of that. Wanted to briefly talk about integrating in situ modeling and remote sensing fields. So using having more of a conversation about how we can integrate our data and modeling results. And models can tell us about where we need to focus our observational priorities based on if the model spread is highest in this region or time period. Maybe we need more observations there. And then also how we can integrate and reformat our data products that we get from remote sensing observations to better inform new model parameterizations. I'll skip that. Yeah, okay, and then I'll leave the summary up, but yeah, I'll leave that up so we can discuss. Thanks.
Thank you, Ellen. Questions?
Hi, Ellen. Ethan Campbell. It's great talk. I have two kind of wonky questions. One is, so for your linear sea ice concentration estimates, it feels like such a valuable result for the community because so many of us use the passive microwave sea ice concentrations. And I'm curious, I guess ideally there'd be some correction factor we could apply to passive microwave to make it reflect the actual sea ice concentration a little better while capturing the benefits of daily resolution. And given the fact that your work shows that high bias, and knowing that the algorithms that the passive microwave data goes through, they get truncated at 100%. There are these distributions that go over 100 and kind of gets truncated there. Do you think that there's some opportunity there to compare the two and create a correction factor that might actually be usable?
You mean to correct it so that it's not over 100?
To correct the passive microwave data so that it reflects the linear sea ice concentrations.
Yeah. I think that's definitely a good next step, and I think it would be very specific to time and also region, perhaps. But thinking about like the winter specifically, I think it does make geophysical sense that the passive microwave data isn't seeing these small leads, and so maybe using LIF in those cases would be more valuable. But yeah, there are also a lot of limitations to the linear ice fraction too. So I don't want to make any like broad statements about where it's better or where it needs to be corrected, and that would take like a lot more investigation into those specific scenarios.
Gotcha. I have a second question too. Also, I guess in the news about a month ago, we found out that the DoD is restricting access to a lot of the passive microwave data that feeds into the climate data record for sea ice concentration. That NSIDC is no longer updating that on a regular basis. I'm just curious, as a community, is this something we should be concerned about when it comes to this really critical data record?
Yeah, I really am not the person to speak to this. Maybe someone at NSIDC would be better, but yeah, it's concerning to me. Yeah. Sorry, I don't really know.
I think the panel that Paul announced that we're going to have on Tuesday, July 1st, is really timely with that. So yeah, more discussions to have. I don't think we understand all of the ramifications yet of what that decision means, but certainly feels like it's impactful.
Do we know if AMSR 3 is going up soon?
I personally don't,
Okay.
but
Slated to launch this month.
We have plenty of time for questions. An online question. Gavin, go ahead.
Thanks. A great introduction to all of that. I was going to make the same point. So there was an announcement from Copernicus today that the DMSP data is going to stop on the 30th of this month, and that they are recommending that people move to their other products. But it's not obvious to me that the other products have the same longitude or continuity that the current NSIDC passive microwave records have. But they also mentioned that there's a new satellite which is retrieving data called the WSF, which should be usable, but that's also being run by DoD, but it's not obvious that anybody has access to that outside of the defense community. Do you know anything about that?
me personally, no, but I open it up to anyone else that does know more about that. I mean, I guess so. The DMSP ones are the SSMIS ones, and so those are kind of what our CDR is based off of. Our long-term climate data record is based off of right now. There are the AMSR-2 and AMSR-E satellites that do have passive microwave data, but would need to be incorporated to kind of reconcile the long-term record with new observations.
Thank you.
Thanks. Nice talk, Ellen. Fighting with the microphone here. So I know you've thought a lot about flow size distributions.
Yes.
And how you can use those to sort of understand what our models are doing CIS process as well. Can we do similar things with melt pond size distributions? I think people have thought about this before, but I don't know if that's really the right quantitative way to get at this question.
Yeah, I've been thinking about melt pond distribution for the ideas of under ice light, right? So if you have a bunch of really small melt ponds that are, so you can have two surfaces that are the same melt pond fraction, and one could be a bunch of small melt ponds spread across the surface, and the other one could be like one very large melt pond, and those would give you really different under ice light fields. And if you have these light limited biological processes that are happening underneath the ice, that is really important for understanding that. And so I have I have been looking at melt pond distribution. Haven't really found a lot of like big trends or patterns based on the airborne imagery that I've looked at, but it's certainly a path for research, and uses the same kind of processing that we use for flow size distribution.
Nice. And just maybe very quickly, how do models that are at relatively coarse resolution capture this? Do they just have a single concentration in a grid cell for melt ponds?
Marika, Alice? That is my understanding.
No, that's
Okay.
wrong. I'll talk about this more tomorrow, but we have an ice thickness distribution, and we have fractions of melt pond coverage for each of those different thickness categories. A lot of times what you'll see is just a grid cell average, but that's weighted, but we actually do the subgrid scale calculations.
Well, that's in the continuity of the previous question then. So given that many CS models, I mean, several CS models now have this capability of simulating melt ponds explicitly, do you envision a possibility to assimilate observed melt ponds in models for prediction purposes, for initializing the CS models? Or do you think that there are still too many problems in terms of scales or maybe definitions for this observation to be taken up in large-scale CS models?
I think the aerial spread of melt pond distribution at a resolution that would be useful is not where it needs to be assimilated into – to models that don't represent individual melt ponds, if that makes sense.
Okay.
Okay.
Thanks.
Thanks.
Well, that's in the continuity of the previous question then. So given that many CS models, I mean, several CS models now have this capability of simulating melt ponds explicitly, do you envision a possibility to assimilate observed melt ponds in models for prediction purposes, for initializing the CS models?
Yeah, thanks, Helen. I'm really curious about kind of your last bullet point here. I know you mentioned like the goal is to use like ice imagery to like help navigate, and I personally have benefited from like ice imagery to get out of very thick sea ice. But I'm curious about if there are industries that are already like doing that like just by routinely, or if it is like a something people wait till there's an emergency in for most systems.
Yeah, I mean, the Navy in the National Ice Center are doing like near real-time support for navigation in the Arctic. But is your question about industry or
Anybody? Yeah.
I don't know in like a systematic like way, but yeah, that is something that we're looking at for, and this is maybe going into my other bullet point about fusing different types of data from different sensors or different modes of observing the ice to understand like near real-time ways to navigate through the ice. We're working with the Office of Naval Research for this specific project on real-time data for navigational support.
That's really cool.
Yeah, I just wanted to follow up on that previous question to ask what would you envisage would be needed from a satellite observational perspective to get the kind of spatial coverage of melt pond distribution such that that information could be either assimilated or better, I don't know, empirically parameterized based on observations and models? Is like more time with ISAT-2 enough, or are different spatial structures needed?
Yeah, okay, so there's a lot of limitations and things that would prevent that, I think. So ISAT-2 only resolves the really large ponds in terms of depth, and also has to be very flat surface to be able to penetrate and not just get returns from the surface of the melt pond. So ISAT-2 is definitely not comprehensively measuring melt ponds and would not be a good estimate of melt pond fraction. Can give ideas of the depth of melt ponds for large melt ponds. Imagery is limited by cloud cover and polar night. Well, there's also not melt ponds in polar night, but the cloud cover in the summer Arctic is a lot. And then I guess SAR is an option, and so there are some studies and people looking at melt pond signatures in SAR, but again, SAR is just like complicated, and so I don't know if that is like a near future Arctic-wide SAR. There are studies that are looking at like, so maybe the pixel size of a satellite measurement is larger than a melt pond, but you can kind of do an unmixing algorithm to determine the melt pond fraction within that pixel. That could be useful, but I don't know if assimilation of melt ponds is useful for models. From the modeling side, I don't know how to answer that question, but.
Oh, yeah, I guess maybe not. Maybe I made an error by referring specifically to like model assimilation, but you know, I'm happy to also hear comments like more broadly about what would be needed to actually get I don't know, trends or something more solid in terms of spatial distribution than what is currently available. But I think you kind of addressed that. That's great.
Thanks.
We still have time for questions, but I'll ask one, give you guys time. So I'm curious, you know, given all of the remote sensing capabilities that we have, what are the limitations of what would you like to be able to do with to understand about sea ice that we can't right now because we're limited by the remote sensing capabilities?
Yeah, okay, so I figured this question might come up, and I do think that like the community has come up with the best answers, right? So Crystal, I'm really excited for Crystal, so that's a KUK band altimeter, and so the really powerful thing about that is that it can measure, the Ka band is measuring the snow-air interface, and the Ku is measuring the ice-snow interface, and so from that you're able to look at the snow depth on the sea ice and get more accurate measurements of thickness from having those on the same sensor and not having to do like any kind of drift correction or anything like that. So that will be great. Yeah, Helen talked about edge. That would be really cool to get another large swath, three-dimensional sea ice measurements. I am a big fan of the high resolution imagery. It would be great to have more of that that's not commercial and has more like normal systematic kind of coverage instead of tasking and paying for it. Yeah. And that's kind of just based on like my knowledge and my expertise. So I don't know about other aspects of remote sensing that would be really useful for CAs too.
Any last burning questions, or does everybody want to go for coffee and cookies? All right, I'll let you guys off the hook. It's okay. 1 minute left, so thanks, Ellen, again.